The first area that we want to discuss when it comes to a proper enterprise campus design is, let's go ahead and focus on first the media. Yeah, we'll start at a logical place, right? We'll go ahead and start with the underlying physical media that we are going to find in the typical enterprise LAN design. The media that we know dominates the local area network is our Ethernet media. And certainly there are many, many flavors of Ethernet, including Ethernet standards over fiber optic. Obviously, what's exciting about this is we can achieve gigabit Ethernet speeds over these particular media options. Notice that when it comes to the Ethernet naming conventions and standards, we know that we do have an indication of the speed in the name. So watch out for that simple fact in CCDA certification. If we are asked for the speeds of these technologies, that's a great simple question for us, because we know, for instance, 10 base T, we know this is technology that operates at a whopping 10 megabits per second, whereas 100 base TX operates at 100 megabits per second, and 1000 base LX, for instance, is gigabit technologies. So we have an indication of the speed right in the name of the particular technology. Something that we need to be aware of with Ethernet is the fact that Ethernet functions utilizing something that we call carrier sense multiple access with collision detection. Carrier sense multiple access with collision detection controls who gets to talk or communicate on the network. By the way, this sounds like a bunch of just technical mumbo jumbo, right? When you initially say it or when you initially first read it. But I want you to go ahead and break down these communications. Break down these communications and you'll be able to understand it much, much better. Carrier sense, meaning the device can listen, can detect communications on the physical media. Multiple access means many devices can communicate on the network media simultaneously. They can't talk at the same time, but multiple devices can access the particular media. And then collision detection, there's a process ingrained in this protocol where it's going to try and detect collisions and based on this collision detection, come up with some type of solution for communicating. We're going to talk more about this, of course. So CSMA CD is the technology that we find with Ethernet. So this is a technology that is key in our local area networks, because our local area networks are typically going to use various flavors of Ethernet. And by the way, what flavors of Ethernet that we engineer in is typically going to depend on where we are in the topology. So what you'll often have is you'll have, due to the aggregate bandwidth, you'll have like fast Ethernet out to the workstations. Okay, so we'll have like fast Ethernet connecting the workstations at the access layer. And then as we move up to a multi-layer switch, we might have a 1 gigabit per second connection. And then as we get into the network core devices, we might go up to 10 gigabit per second connections. So notice, due to the aggregation of bandwidth as we move throughout the infrastructure, we need to typically increase the bandwidth capabilities as we move from our access layer to our distribution layer to our core layer of the network. Remember, you need to be able to handle the aggregate bandwidth. Here, where the device connects to the layer 2 switch, we're fine with fast Ethernet, 100 megabit per second technologies. But then with all these layer 2 connections leading to the distribution layer, we may need to step it up to gigabit per second Ethernet to handle the aggregate effect. And then down in the core, 10 gigabit per second Ethernet to handle the further aggregation of network bandwidth. All of these devices, of course, being powered by this underlying carrier sense multiple access collision detection. This process works like this. Before the station will send its data onto the network, it will wait and listen. This listening period is controlled by a randomized window. Okay, so there's a randomized amount of time that the station is going to listen. If it detects that things are clear on the wire, it will go ahead and transmit. So we'll listen for a randomized period of time, we'll then transmit. Now, you can have a hub-based network, and we'll elaborate on hubs here later on today, and we'll remind ourselves why hubs are so bad, why we're moving away from hubs in our environments. Hubs are going to create a totally shared media where collisions can and do occur. When there are collisions, notice, stations will wait for another randomized time period, and then they'll go ahead and retransmit. So there's randomized timing intervals in here, and that helps if there is collisions for stations to be able to transmit successfully on the network. Now, CSMA CD is what we want to be intimately familiar with for how our LANs are going to function, right? How the local area network is going to function. But there is another approach that I want you to be aware of, and we will cover when we get here later on in the CCDA course. There is another option. It is CSMA CA. And the CA stands for, instead of collision detection, CA is collision avoidance. So another fundamental approach can be utilized here called CSM CA, collision avoidance, and we'll look at this again when we discuss wireless local area networks. So our local area networks are based on a collision detection process, while our wireless local area networks are going to be based off of collision avoidance technologies. By the way, we no longer focus on token ring because token ring is disappearing from networks, but it was also another classic collision avoidance type technology. So, we may have thought we were done with collision avoidance when token ring died off of our networks, but now collision avoidance does rear its head again, and that is thanks to wireless local area networking technologies. Now, the technology that we love to engage in our enterprise local area network designs, I've talked about it several times now in the course. It's obviously important for you to master. This technology is EtherChannel. And boy, oh boy, one of the reasons that we love this particular technology is the fact that we can take care of those aggregate bandwidth needs that we alluded to. Thanks to aggregation of ether channeling, we can really accommodate that aggregate bandwidth that we spoke of. Remember, we have these layer 2 access layer switches, and they're feeding into the distribution layer, which is feeding into the core of our network. Now, in the core, we have to accommodate this aggregate bandwidth, right? So one of the things that ether channeling will allow us to do is to bundle together these links between devices in the core of our network. This is so awesome. So this might be our 100 megabit per second technology. This might be our 1 gigabit per second technology. And then we can bundle together these 1 gig links in the core and effectively create 4 gigabit per second links between these devices. Isn't this a great way to pull off this aggregate bandwidth requirement as we get into the core of the network? Now, one of the questions that I get asked all of the time whenever I discuss EtherChannel, and I can understand why students would immediately want to ask this, they get excited by the EtherChannel capabilities here, and they immediately just start thinking, wow, this is so awesome. How many links, right? How many links can we bundle? And this is indeed going to be Cisco platform dependent. The answer does indeed depend on the Cisco platform, on the Catalyst Switch platform that you're working with. They just keep getting better and better with the number of channels you can aggregate. I mean, the answer used to be 2. Then Catalyst switches could support 4. Then it was 8. Then it was 16. I believe some are even capable of bundling together 32 links now. So you really will want to check with the specific documentation of your specific platform in order to make the determination of exactly how many links that you can support in one of these ether channels. Okay, now let's focus in on the ether channel technologies a bit more here. Notice that ether channel, we know it's going to be used to aggregate the bandwidth together. And by the way, you'll often hear of ether channel technologies with some different terms. One of those terms might be NIC teaming, network interface controller teaming. Okay, so sometimes we will see NIC teaming for this technology. As I said earlier when we talked about when we talked about ether channel earlier, a lot of people are fooled into thinking this is a spanning tree protocol feature. It's not a spanning tree protocol feature, but it does relate directly to spanning tree protocol, because what it fools spanning tree protocol into thinking is that these bundled links are just one link between the devices. Remember, thanks to spanning tree, if you were to take 2 Cisco switches and you were to put 2 links between those 2 switches, by definition, spanning tree protocol would come in and it would block on one of those links. This is the built-in loop prevention mechanism that we have with spanning tree protocol. So what ether channel does is it fools spanning tree protocol into thinking that these 2 links are one link, and as a result, there is no blocking on one of these redundant paths. Now, one of the things that we love about ether channel is the fact that Cisco will, of course, load balance across the links, the actual physical links in that bundle. As designers, we need to be aware of the fact that that is going to be based off of the MAC address that we're trying to communicate with on most Cisco Catalyst platforms. Okay, on most of your platforms, it is going to default to the MAC address utilization for the load balancing decision. But we as network designers can implement it where we use something other than destination MAC address. Perhaps in our design, it's going to be more appropriate to load balance based on the layer 3 IP address. Maybe you want to use a more sophisticated combination of MAC and IP. Maybe you want to use just the destination IP or just the source IP address. On your different platforms, you're going to have different options for the load balancing configuration. Let's take a look at one of our 3560s as an example. And notice in global configuration mode, you can say port channel. I think that's the command. Let's see. Let's see. I know it's here in global configuration mode where we can set the different types of load balancing. I'm just looking through the commands that are available here, see if my memory gets jogged. But for sure it was either like port channel or channel group. Hold on here. Let me just use one of our best friends, obviously Google. And I'll just search on EtherChannel. EtherChannel and load balancing should get us what we want. Maybe the keyword Cisco will help us too. Okay, so, yep, the command that, oh, I'm on a router. Yeah, it would help if I was actually on a switch. Yeah, it would help if I was on the right type of device, wouldn't it? Yeah, it sure would. I was right. It was the port channel command, but we need to be on an actual switch, right? We're on a router right now. Awesome. So if we go over to one of our switches and we say in global configuration mode, port channel, notice we do have options for load balancing. And those options are as follows. On this particular device, so we do want to remember that these capabilities are indeed going to be switch dependent. But notice on the 3560 here, it's pretty robust. Load balancing based on destination IP, destination MAC, source destination IP, source destination MAC, or just source IP or source MAC. The default on most platforms, as I indicated, is going to be destination or source MAC. But we can manipulate that, and this might be something very, very valuable for us to tweak in our design. You can do network management software, performance management software on the Ether channel, so you can monitor the Ether channel, and when you do, perhaps you find out that the links in the bundle are not being effectively load balanced. And that's when we would want to manipulate the particular load balancing that we are doing. One of the things when we design these ether channels, we have to understand we are introducing a new type of interface on the device. The interface that we are introducing is a logical, what's called port channel interface. These are abbreviated. You know how we're going to have our abbreviations, like we have fast Ethernet, for instance, 0/0. Well, for this in the operating system, we have PO, like port channel 2. So PO is the abbreviation for our port channels, and this is the logical link. And this is how spanning tree protocol is tricked. For your 4 physical links, let's say, if you were to bundle together 4 physical links, these would get bundled together in one logical port channel. For our EtherChannel implementers, the command channel group is what they use under the physical interface in order to have these links bundled under the port channel. So our physical interfaces are going to belong to this new logical port channel interface. Now, when you're designing an ether channel, you have to make sure there's compatibility between these member interfaces. And I always like to point to the terrible 1980s movie, Twins. We just got to remember that Danny DeVito and Arnold Schwarzenegger disaster of a movie called Twins. The movie Twins reminds us that the ports need to be identical in their configuration. So when we are configuring these ether channels, we need to think in terms of, okay, for the physical interfaces, we need the same speed. We need the same duplex. We need the same allowed VLAN list. We need the same access port config or trunk port config, etc. So the big design caveat here is that the parameters of your interfaces are identical in their configurations so they can be properly bound together in this logical ether channel. Now, realize that thanks to the different types of catalyst switches we can have, for instance, layer 2 only versus multi-layer catalyst switches, we can create ether channels that are based on layer 2 links. Or we can create ether channels that are based on layer 3 links. And by the way, we have multiple options for our layer 2 ether channels. We could have access ports, layer 2 bundled together, or we could have trunk ports, our inter-switch link trunk ports, or 802.1q trunk ports. We could have those bundled together to form this ether channel. Another great option for ether channeling is to go ahead and ether channel together your routed ports. So we can take layer 3 routed ports on the switches and we can bundle those together for one big aggregated router port on one of these multi-layer switches. Remember, it's going to be platform specific as far as how many particular interfaces can be bundled together under these different configurations. But the great news is all of the time, it seems like all the time we see periodically Cisco announcing that they've increased the number of links in the EtherChannel bundles for their more modern switch devices. Now, we have the two different overall options, right, for creating the EtherChannel, a layer 2 bundle or a layer 3 bundle. And then there's 3 ways in which the EtherChannel can be negotiated. You can go in and you can say, I don't want any help with the formation of my EtherChannel. And this is designing EtherChannels that are to use what's called the on or static mode. Okay? So there are 3 modes that we can choose from for creating the EtherChannel. There's the static on mode, and this means that we don't want any dynamic negotiation to take place. The default technology, however, that's proprietary to Cisco and the default on most of their equipment is for the port aggregation protocol to be used. Port aggregation protocol makes it a bit easier to create your EtherChannels. What you do is you end up going over to one side of the bundle, one side of the link, and you set the mode to what's called desirable. The PAG-P mode of desirable. That's all you got to do is go over and set that mode on the EtherChannel. And now what happens is that mode will send out these PAG-P messages to the other side, and the other side will automatically engage in the EtherChannel. Now, the PAG-P, the port aggregation protocol approach, is, like we said, Cisco proprietary. And we know the word proprietary is a bad word when we're implementing and designing networks. As an alternative, we really seek technologies that are non-proprietary, that are open standard technologies. And the open standard version, if you will, of the PAG-P protocol is the link aggregation and control protocol approach. This is the official IEEE standard of 802.3 AD. Notice it works very similarly. Instead of the desirable and auto keywords that are used with PAG-P, it is the keywords of active and passive that are used with LACP. But the same basic concept. We would go to one side of the links and we would use the keyword active in order to initiate the LACP negotiation of the EtherChannel. By the way, when you're designing these EtherChannels, we need to make sure the implementers understand what we want to do by way of negotiation, because if you were ever to do an incompatible negotiation, this is an area where you can literally create layer 2 loops. Remember, we're fooling around here with something that impacts spanning tree protocol. So we need to be very, very careful. If we're going to manipulate something that impacts spanning tree protocol, it could mean that we are going to introduce loops in the network. So we got to really watch out when we create these EtherChannels and make sure we're doing the modes correctly. So when we're designing our EtherChannels in our design document, we'll want to ensure that we do proper documentation for the EtherChannel configurations. Where exactly we are going to create our bundles, what interfaces are going to be involved, what locally significant port channel identifier is going to be used, and you'll want to decide on the particular mode. For instance, maybe we're going to set the desirable mode on this side of the links, and then maybe we're going to leave the default PAG-P of auto on this side of the links in order to form these ether channels and experience the aggregate bandwidth effect thanks to our ether channeling. Well, congratulations, you survived another lesson here in our CCDA course, this one focusing on LAN Media. And of course, the big technologies here we discussed were CSMA CD and EtherChannel technologies. What we'll be doing next, by the way, in our Enterprise LAN lesson is we'll be taking a look at LAN hardware options. We'll talk about the differences between things like repeaters and hubs and bridges and switches and routers. So we'll take a look at devices that we're going to find today in the enterprise LAN, and we'll talk about the differences between these devices. That's next up. Before we do any of that, though, we want to cover what two types of ether channels can be created and what are the three options for their creation. Go ahead and chat your answers in the question and answer area. What two types of ether channel can be created and what are options for the creation of these two types of ether channel? Awesome job. Awesome job. So we've got two types of ether channels that we can create. We've got the layer 2 ether channel. We've got the layer 3 ether channel. By the way, as far as the layer 2 ether channel goes, that might be utilizing trunk connections, or it might be utilizing access port connections. Now, for layer 2 or layer 3 ether channels, we have three modes we can use to create them. That would be the on or static mode. That would be the PAG-P mode. That's P-A lowercase g uppercase P. And finally, there's the LACP, standards-based negotiation approach to the creation of your ether channels. So lots of different options when it comes to the creation of your ether channels. Layer 2 options, a layer 3 option, and then for all of those methods or types of ether channel, we do have different modes to create both layer 2 and layer 3 bundles of links.